to look at systems of inequalities. Now, last class period, we discussed systems of quadratics and how to go about solving those. Today, we're going to look at quadratic inequalities in systems. The three basic steps that we're going to use to graph are the following. Step 1, we're going to graph the parabola with an equation y equals ax squared plus bx plus c. We also know that as standard form. We're going to make the parabola dashed if it's less than or greater than, and we're going to make the solid less than or equal to or greater or than or equal to. We're going to test a point, which means we pick a point inside or we could pick outside the parabola to determine whether the point is a solution of the inequality. We're going to shade the region inside the parabola if the point from step 2 is a solution. Shade the region outside if it is not a solution. So basically what we're going to do is just like when we did linear inequalities. We're going to graph. We're going to pick a point either inside or outside the parabola. We're going to test that point and see if that point works. We are going to shade the true region, and then when we get to systems, we will find their overlapping region, which is called their feasible region. So for the first step example we're just going to do a basic inequality. We're not going to do a system. So step 1, write it as y equals, or look at it as y equals. Now this is standard form, so if you remember how to find the vertex for standard form, you have to do x equals negative b over 2a. Now b is my value in front of my x, and since it's a negative 2, a negative becomes a positive 2. 2 times negative 1 is negative 2. So 2 divided by negative 2 is negative 1. Then we take that negative 1 and we substitute it back in the equation every time we see x. We evaluate that using our brain or our calculator, and we find the answer of 0. Okay, now we have the capability of graphing. So there's 2 pieces of information we need. We need the vertex, and then we need to create a 3-column table. My leading coefficient is negative 1, so when I make my table, I will use negative 1 as the 3rd column. When completed, we get a vertex of negative 1, 0, because we found a negative 1 and we substituted it in and found 0. And then here's my table. So now what I'm going to do is I'm going to slide this down and show you what the graph looks like. So we plot negative 1, 0, and then we go out 1 unit and down 1 unit. Now, since the equation was less than, it is considered a dashed or a dotted inequality. So it looks something like this. Now, at any time, if you need to, you can pause the video to catch up, or you can play back if you miss a step. Once we have the region, we can decide whether it's inside or outside. Now, the easiest point to pick on a graph is 0, 0. And if you look, 0 exists actually on the outside or the exterior of my parabola. So I'm going to test 0, 0. So everywhere I see and x in my original problem, I'm going to put 0 in. So I'm going to do that. Once I do that, I get something that looks like this. I evaluate the right-hand side and I get 0 is less than negative 1, which is not true. That is false, people. So 0, 0 does not work. So since 0, 0 does not work and it's on the outside and we shade the true region, we're actually going to shade the interior of the graph. What this represents is the fact that I could pick any coordinate inside the graph and substitute it into the math problem and it will work. But I cannot pick any point on that parabola because it's dashed. It's like a boundary, but we can't pick anything there because it will not work in the problem. Nor will anything work on the exterior of the problem. So hopefully this is a good review of how to graph an inequality. The next problem we're going to do is going to be a system. And here's the system. It looks like a lot on one page, but I had to squeeze it all into one page. Now, I tried to color code this So green is going to be my first parabola, and blue will be my second parabola. So first I imagine it's an equal to sign, and I do negative b over 2a. Now b in this one, since there's no b value or x, is 0. So it's 2 times negative 1, which is negative 2. So it's 0 over negative 2, which is 0. Once I have done that, I substitute it back into the equation where I see x. So I get negative 0 squared plus 3 is 3. So I calculated 0 for my x, so that's my 0. And when I substituted in, I got 3. So my parabola is going to begin at 0, 3. Now my leading coefficient's a negative 1, so we create our table. Negative 1 being our last column. I use 1, 1 squared, 1, and 4. Okay, we're going to make that negative 1 and a negative 4. So then I plot that. So I'm going to grab my graph that I have hiding down here. I'm going to go to 0, 3. I'm going to plot a point. And then I'm going to go out 1 unit, down 1 unit. And I will go out 2 units and down 2 units. I graph it in. Since it was not equal to, it is dashed. All I have left to do is shade a feasible region. So this time I picked a point, and the point I picked was 0, 0, which was actually inside. So the question is 0 less than negative 0 squared plus 3? Which it is. 0 is less than 3. So this time, the interior is what works, so we shade the interior because it was true. Now remember, my graph extends longer, it's just my graph is kind of short here. I repeat the exact same process for my second equation. I imagine it's y equals x squared plus 2x minus 3. I plug in my negative b over 2a and I evaluate, finding the answer of negative 1. To find the rest of my vertex, I take negative 1 and substitute it in my math problem everywhere I see an x. Negative 1 squared is 1. 2 times negative 1 is negative 2. So 1 minus 2 is negative 1, minus 3 more is negative 4. So my vertex is at negative 1, negative 4. Now this does have a direction of open being up. The value in front is a 1. So I create my table. I use it to find my stretch. Remember, if your a value is not 1, you're going to change that and multiply by that value. So now I can graph it. So I'm going to plot at negative 1, negative 4. It's kind of hard to see here. I'm going to go over 1 unit and down 4 units, which is about right there. I'm going to pick a point inside or outside that blue region. Now 0, 0 exists interior this time, so I'm going to test that. If I put 0, 0 into my original problem, I get 0 is 0 greater than 3. Well, in this case, 0, 0 is greater than 3. No, it's not. It's greater than negative 3. This should be a minus here. You're probably guessing, how did that end up being a positive? Okay, 0 is greater than negative 3, so that is true. So 0, 0 works. So this time I would shade the inside. Now, on your paper, it's probably easier to see where the two overlap, because it's just like a Venn diagram. Where these two actually overlap is in this lovely little kind of elliptical oblique shape right there in the middle. That is my feasible region. If I pick anything on the solid line that's connected to that feasible region, it will work in both of them. If I pick any ordered pair on the dotted line, it will not work in at least one of them. If I pick any point in the shaded region, it will work for both of them. So I hope this is helpful. Let's do one more example so we can try this one more time. And then I'll have you work on some on your own. The two I'm going to do this time don't look that hard, but they're missing a bunch of stuff. So that's why we're just talking about these. If you look at the first one, I have y is less than or equal to negative x squared. So it's the parent function, but it's a reflection across the x-axis because it's negative. If I do x equals negative b over 2a, my b value, since there's nothing at the end, is 0. So it's 0 over 2 times negative 1, which is 0. If I plug 0 back into that, I get, of course, 0 as an answer because it's just a reflection of the parent function. I create my table using negative 1 because my value in front is negative 1. 1 squared is 1 times negative 1 is negative 1. 2 squared is 4 times negative 1 is negative 4. And I plot those points. Now this time, it says less than or equal to. Since it says less than or equal to, it's going to be a solid graph. Looks something like that. Plot 0, 0, go out 1, down 1, out 2, down 4, and reflect. Now I'm going to pick an other ordered pair. Now this time I can't pick 0, 0. So I just randomly picked an ordered pair that existed on the outside, 2, 2. You can pick something on the inside as well. So I put 2, 2 in the problem. Oh, there's a typo right there. Is 2 less than negative 4, which it's not. So 2, 2, which would have been on the outside, does not work. So if it did, I would shade the outside. But since it doesn't, I'm going to shade the inside. I'm going to grab my little shading tool here. I'm going to repeat the process with the second one, noticing I'm missing B. So I do negative B, so 0 over 2 times 1, which is 0. I substitute that back in is 0 squared minus 3. So I get 0, negative 3. This time the A value is 1. So I create my table and I graph it. Now it didn't say equal to in the original problem. Since it didn't say equal to, when I graph it, I'm going to use a dotted. So I'm going to go to 0, negative 3, and I'm going to graph them. Now this time I can pick 0, 0 because 0, 0 is inside my graph right here. So I'm going to test it. Is 0 greater than 0 squared minus 3? Well, 0 is greater than negative 3, so that is true. So that one does work. So it's up and above this time. What happened to my little tool here? So where the two overlap this time is what's in the middle. Right there. Now, Mrs. Doran, is it always going to be what's in the middle? No. Okay. You could have two graphs that are completely separate, and one you shade up, one you shade down, and they have nothing in common. So it's no solution. You could have two graphs where one is nested inside the other, and what they have in common is just a little band of graph. So be very careful. You shade in dark or erase the other amount. You're looking for the feasible region, the part where they overlap. I hope this is helpful, and I hope I've gotten you used to the idea of graphing systems of inequalities when they are quadratics.